Hey guys, good to be with y'all today. Our topic for the day is going to be a kind of refresher course on the geometry or shapes that different molecules take on. And so what we're going to do while you've just had that refresher on how to draw just kind of basic chemical structures, we're going to start with small molecules and kind of reintroduce some of those key terms like geometry, polarity, different things like that. That way we can start applying them to larger, more complex molecules along the way. And so what we see is that even though we tend to draw structures in 2D in chemistry, we've got pencil and paper, the molecules themselves are not really flat. So the drawing looks 2D on the left, but if you'll look over here on the right, we see that the molecule itself is actually in 3 dimensions. And we've got little atoms kind of pointing in all different directions. And so we're going to do a brief review today of kind of the names of some of those shapes, because eventually what we're going to want to move on and be able to do is take a look at the shapes that are present within a larger molecule, kind of like this caffeine molecule on the screen. We've got several tetrahedrals, we've got several planar portions, and we want to be able to analyze a molecule kind of from end to end and classify those shapes. Because what happens is the shape of the molecule plays a big part in how it reacts. And that affects functions in our body. It affects just tons of things that we see in our world every day. So I'm going to take you to this little sheet right here. If you've had me before, this chart kind of looks familiar. But when we start by asking the question, well, why do molecules take on certain shapes? One possible explanation that has been offered for that is what's called the Vesper Theory. It's an acronym, VSEPR, and that stands for Valence, Shell, Electron, Pair, Repulsion Theory. And so we know that in chemistry, the bonds are formed from electrons. And so what happens is those electrons, since they're all negatively charged, they try to orient themselves as far apart as possible in order to minimize the repulsions generated by having 2 negatives close together. So the farther apart those electron pairs within the bonds can get, the better. Now there's also another kind of subset of this theory that lets us know that lone pairs, which are our unshared pairs, and if we take you back to the molecule, we kind of refreshed on this recently, that would be the 2 little dots, those are lone pairs. They tend to repel more than shared pairs in a bond. And so what that does, since the lone pairs repel more, if there are both lone pairs and shared pairs, aka bonds, in a molecule, the lone pairs tend to kind of bend or push those bonding areas down. Now, when we're looking at geometry within Vesper Theory, there's 2 ways that we can classify it. We can either classify the geometry based on the electron regions. And what we do is we simply look at the central atom and we count the number of electron regions around the center. And that's anywhere we see electrons. It could be a lone pair or it could be a bonding area. So if we were to do that for our little sample water molecule here, our central atom is oxygen, so we would count around it and see that we have 2 bonds and 2 lone pairs. That gives us a total of 4 electron regions. Now the way we classify electron regions is in this top box on your chart. So this top row right here gives us the distinctions for classification by electron region. So if you have 4 electron regions, electronically you have a tetrahedral shape. Tetra referring to 4. If you were to have 3 electron regions around the atom, again, that could be just bonds, that could be bonds and lone pairs, then your electronic geometry is trigonal planar. If you have just 2 electron regions, your electronic geometry is linear. Okay? Now, what we oftentimes end up spending more time on in organic chemistry is what's called the molecular geometry. And that's where we take into account that second part of the Vesper theory that lone pairs repel more. And so it's going to account for that overall shape of the molecule based on the bonds and whether or not they're being pushed down or bent by lone pairs. So while the electronic geometries are reserved to this first row in our table, the molecular geometries can be anything on the chart. And typically, for our purposes in organic chemistry, we'll kind of stay to the left of this line here, so kind of in the 2 regions, 3 regions, 4 regions. And what we're going to be looking at is if there are lone pairs, how do they affect that overall shape? And so let's start with this 4 regions column over here. So if you have a center atom and there are no lone pairs whatsoever, that means you've got 4 bonds. And so electronically, your geometry is tetrahedral, but that also means from a molecular standpoint, it's tetrahedral as well. That molecule has 4 bonding regions evenly spaced apart. Now, let's suppose that you still have 4 electron regions, but one of them is now a lone pair, and 3 of those regions are bonds. What that lone pair is going to do is repel those bonds kind of down into almost a tripod or a pyramid-shaped structure. And so molecularly, it's going to be called a trigonal pyramid, a pyramid with 3 points. So electronically, it's tetrahedral, but molecularly, it's trigonal pyramid. Then, if we proceed down to the last one, which kind of matches our water molecule, where we have 2 bonds and 2 lone pairs, the geometry there is going to be bent. And so I'm going to pull up a simulation right quick, just so we can visualize a few of these, since we aren't in class together for me to hold up some models. And so here we have an atom that's in the center. We've got our purple marker there on the center atom. And we happen to have 2 electron regions, one on the left and one on the right, and they're both bonds. So let's start with our electronic geometry. 2 regions is referred to as linear. Now, as long as you don't have any lone pairs, your electronic geometry and your molecular geometries are going to be the same because there's no change in the overall shape since there are no lone pairs. Now, let's add another bond to get us up to 3 electron regions. 3 electron regions is referred to as trigonal planar. Now, in this case, when we're looking at our center atom, there are no lone pairs to change the shape. So that means both electronically and molecularly, it will be trigonal planar. Now let's suppose that we remove one of the bonds and replace it with a lone pair. The center atom is still surrounded by 3 electron regions, 1 lone pair plus 2 bonds. Electronically, it's still trigonal planar. However, if we now consider the overall shape of the bonding regions, it looks like it's been pushed down into a V by the lone pair. So anytime you have 2 bonds being pushed down, that's going to generate a bent molecular shape, a bent molecular geometry. Now, let's go ahead and look at this example. Let me get 3 bonds on there. So now what we have surrounding our center atom is a total of 4 electron regions. So electronically, it's tetrahedral. There are 4 regions. However, one of those regions is a lone pair, which means those 3 bonding areas are going to be repelled downward into a pyramid shape. So if we're just looking at the overall shape of the bonds, it's going to be trigonal pyramid. And then we could, if we wanted to, take off a lone pair and go back to our just 4 bonds. And as long as there's no lone pair, both electronically and molecularly, it's going to be tetrahedral. If I replace 2 of the bonds with 2 lone pairs, that gets me back to my water molecule. Electronically, it still has 4 regions, which is why the electronic geometry is tetrahedral. But molecularly, those lone pairs repel the bonds, pushing them down into a V shape. So we would classify the molecular shape as bent. So let's go ahead and go back to our notes here and give this a try, just filling out this little chart. And so I'm going to draw the structures quickly for us since we recently practiced that. And then we're going to go through and practice classifying our molecular and electronic geometries. And what we're really trying to do kind of by the end of this chart is we want to develop a good sense of what I call 3D brain. And what that is where even though you may see the structure in 2D, I want us to start practicing thinking about that structure in 3D. And so on the left-hand side, I'm just going to draw the structures in 3D, like you might if we were doing the simple Lewis structure. Put these guys in there. And then last one, BF2, or I may have one more. I need to keep scrolling, don't I? Oops, yes, I do have one more, good deal. And then BCl3, there's our boron exception, typically forms 3 bonds. All right, so now those are ready for us, and we can just kind of knock out this chart really quickly. Okay, so first it asks us to figure out the number of electron regions around the central atom. Our central atom here is carbon, so it appears that we have 4 electron regions surrounding our center atom carbon. So if we go back to our chart, if we have 4 electron regions, that's going to be referred to as tetrahedral. So electronically, this is a tetrahedral molecule. Now, it's kind of getting us to think, do we have any lone pairs that are going to affect the shape? We have no lone pairs, so that means the molecular geometry will remain tetrahedral. And what we're going to do is practice redrawing the 2D structure to try to reflect the 3D geometry a little bit better. So a tetrahedral shape, we're going to have our hydrogens kind of pointing downward and 1 hydrogen at the top. And so if I take you back to our simulation right quick and let you just see what that looks like. There we go. So I've got kind of my 3 pointing down and my 1 to the top. Or sometimes later on we'll learn that you can draw a tetrahedral kind of like a person doing the splits with their hands up in the air. But we'll get to that a little bit later. All right, so now let's do our next one, H2O. So start with electron regions, 1, 2, 3, 4. 4 electron regions corresponds to a tetrahedral electronic geometry. But in this case, we do have 2 lone pairs. And so what that means is those lone pairs are going to repel more, and so the overall molecular shape of the bonds will not be tetrahedral, but rather bent. 2 bonds that are being pushed down form a bent V shape. So when we redraw our water molecule, we want to draw those hydrogen bonds as if they're being pushed down or bent. Next, we've got carbon dioxide. And so we're going to count our electron regions around the center atom. Now remember that if you have a double or a triple bond, that still only counts as 1 electron region. It's 1 area where the electrons are, even though you have more electrons present in that space. So even though they're double bonds, they just count as 1 region. So with that in mind, here we have a total of 2 regions around the center atom. Electronically, when we have 2 regions, our geometry is going to be linear. There are no lone pairs on the center carbon, Therefore, the molecular geometry will remain the same. Linear looks like a line, so we want to make sure that our structure is matching that, where we have the oxygens in a line with the carbon. All right, last three. So here we've got PF3, and we want to look and classify the electron regions around the center atom. Here we have 4 electron regions, which means that it's tetrahedral. Now, out of those 4 regions, one of them is a lone pair. 3 of them are bonds. When you have one lone pair pushing down 3 bonds, that molecularly is classified as trigonal pyramid. Those bonds form a 3-pointed pyramid shape. So we'll write that in for our molecular geometry. Now again, the way we draw the structure should start reflecting the shape. So those bonds we want to draw pointed down in kind of a pyramid shape. And you'll notice that this resembles the first tetrahedral that we drew with carbon, except it has a lone pair at the top instead of another bond. All right, last one here. So if we look at our BeF2, again go to the center atom. Here we have 2 electron regions, which corresponds with a linear geometry. There are no lone pairs, and so the geometry molecularly will remain linear, and we'll draw our atoms in a line to represent that. And what you've probably picked up on is if a molecule is classified as linear electronically, it's going to remain linear molecularly. Now, final one, we've got boron in the center here, and we have 3 bonding electron regions. 3 electron regions corresponds to a trigonal planar electronic geometry. Now, around the center atom, there are no lone pairs. So that means the overall shape of the bonds is going to remain trigonal planar. It's like 3 points in a flat plane. And so our drawing is going to be very similar to the structure we first drew, because that's already pretty true to shape. All right, so great job on working through the chart. So as you progress through the rest of your activity, I want to kind of give you a heads up on some of the things I'm asking you to do. So during the activity, you're going to be looking at some 2D and 3D representations of molecules kind of side by side. And this is going to sound weird, but here's what I want you to do. What I'd like you to do is kind of look closely at the 2D structure of the molecule, kind of pointing to it here with my little pen. Then what I'd like you to do is kind of look at or compare the 2D drawing with the 3D model. And so if I were just going based off the 2D drawing, it looks like everything should be sticking straight out. But what we really have is kind of 2 tetrahedrals that are connected right there in the middle. And if I rotate it this way, you'll see that one of these bonds is sticking up while the other is sticking down. And so really just kind of rotate that molecule around, get a good feel for it. Then what I want you to do is go back to that 2D molecule, look at it one more time, and in your mind, kind of close your eyes and try to visualize what the 3D shape looks like. And what you're doing in that, I know it sounds crazy, but you're training your brain to think in 3D even when you're looking at a structure drawn in 2D. Now this takes a lot of practice and a lot of time spent kind of doing this. I know when I first took organic chemistry in college, this was hard for me. I didn't think very well in 3D. And so I'd spend a lot of time with my model kit, just building and rebuilding, molecules, looking at them, turning them around in my hands. And so eventually what we're going to be able to do is kind of take a big molecule like this. This is actually the structure of hydroxychloroquine. You may have heard that coming up in the news with relation to COVID and potential treatments. But it looks like a pretty much a flat chain with some rings over here on the left. But we're going to see it has a very complex structure, and that kind of helps it work the way that it does. And so you've got lots of tetrahedrals within this chain. You've got some trigonal planar here, this kind of flat, three-pointed area. And we've got even a bent over here on this oxygen. And so we're going to start incorporating shapes into more complex structures. And so it's good if you can kind of already have that 3D sense cultivated in your brain. So thanks so much, guys. That is all for now, and we'll see you next lesson.